Okay, everyone, this is Hakop Pashayan, and he's going to talk to us today about classical simulation of quantum circuits. Thank you for coming, Hakop. I'll let you take it away.
Fantastic. Okay. Thank you, Salman and Cihan for inviting me. And thank you everyone for being interested in this topic. Yeah, my name is Hakop Pashayan. I'm from Free University Berlin, and I want to talk to you about classical simulation of quantum circuits. I should say this is work in progress, and I don't think you're going to see anything that's kind of groundbreaking, state-of-the-art simulators in this talk. I think there's some cute ideas in here that I want to explore and turn into something that maybe is state-of-the-art. But I thought you're the kind of crowd that might be interested in what I'm going to talk about today. Before I start, maybe I'll just make sure, can you hear me okay? And can you see my cursor? Great.
Yeah, I can see your cursor.
Yeah, sorry, it's white on white background, but I'll move it around so it is useful. Okay, so an overview. Today's talk is going to be in two parts. The first part's going to be small, and it's just going to kind of set the context of classical simulation. And I want to, during the part one, kind of touch on this paper with Stephen Bartlett and David Gross from 2017, because I think that Salman was maybe interested in this result when he first contacted me. So I want to just at least give some very high-level comments about the content. In this part, I will kind of motivate classical simulation and talk about some notions of simulation and how they relate to each other. And then the second part, which will be the bulk of it, I will talk about some kind of general quasiprobabilistic simulator. I'll present this general quasiprobabilistic simulator, and it's mainly based on my PhD thesis and this work with Joel Waldman and Stephen Bartlett from 2015, but it kind of touches on this paper from 2021, and this paper, Seddon et al., that I think James Seddon talked to you guys about maybe last week or the week before. Okay, so let's start with motivation. Why study classical simulation of quantum circuits? I guess there's a lot of good reasons, as you may know, and one of these is that classical simulators give us cheap and immediate solutions to quantum problems. So all sorts of problems motivated by real-world physics. Classical simulators kind of are the go-to for a lot of these. We don't have a quantum computer yet. And quantum-inspired classical solutions is kind of this maybe weird, unexpected application where, like an example is this paper by Ewan Tang, where there was a real-world motivated classical problem. The first solution was a quantum solution. Then later in this paper, they figured out a classical way of solving that problem that was motivated by the quantum solution. So it's surprising that, these reformulating and solving the problem in a different, in quantum language can actually help you find a solution that's classical. Of course, a big motivating problem is that it's a incredibly valuable research tool. So something like the stabilizer formalism is, the bread and butter of a lot of what we do in quantum information. Our understanding of entanglement theory and all sorts of stuff is, these techniques are very important for us as researchers. But something that's motivated me and perhaps motivated some of you is that studying classical simulation helps inform our understanding of the divide between classical and quantum. And I think this is a really interesting aspect. So a lot of the motivation for this paper came from this perspective, where if we imagine a blue box here, that is kind of the set of all computational tasks that can be efficiently solved by a quantum computer, then we have a bunch of stuff on the left here that's like things that are classically simulable. So things like stabilizer circuits, nearest match gates, circuits with positive quasiprobabilistic representations, and so on. And each of these is a classical simulator that takes a chunk out of this set of quantum tasks that's quantum solvable. And so you could kind of think of these as like things that are removed that are not interesting, that don't have like superclassical computational power. At least we'd like to think of them this way. And then these balls on the red balls on the right represent tasks that we know are hard to simulate classically. So some well-known examples are like linear optical networks. So the well-known result of Aronson and Hakop, hardness of boson sampling, also instantaneous quantum polynomial circuits, Bremner, Josar, Shepard, Montanaro have worked on this, and so on. And these kind of cut out, the other end of this box and say this is outside classical. And one would hope that pushing these techniques to the limit, there's maybe some transition that emerges, and it's kind of interesting to ask what is this transition, what drives it, what separates classical from quantum, because after all, the complexity of nature is quantum and not classical. And for a long time, we thought it was classical, and it's kind of the way we understand quantum somehow. But this is maybe an oversimplified cartoon picture, and there's a lot of problems with this picture because even the starting point, these notions of simulation, both on the left and on the right, are not all the same. There's many notions of simulation, and the richness of these notions of simulation is valuable because it gives us more breadth and more ability to attack problems. But it also makes this picture confusing and makes it harder for us to understand what this transition is. So a lot of this paper was about understanding what these different notions of simulation are and how they relate to each other, and what is the right one to use when you want to understand the distinction in computational power between classical and quantum. But in any case, I'm not going to go through all these details, but I want to introduce some notions of classical simulation that might help set the context of the kind of literature or some of the literature in this area. So to do that, I've got to define two key probabilities, this probability PC and this probability PQ. So PC is defined as follows. So if we let C be a description of a universal classical circuit, so some circuit of ands, ors, and not gates, then this circuit could define a Boolean function that takes length and bit string to 0 or 1, yes or no answer. And then we can define this PC as the probability that the Boolean function evaluates to 0 on a uniformly random input. Okay, so perfectly well-defined probability for every input circuit C, and also one that can be estimated by having access to the classical circuit. So you could simply run the circuit lots of times on random inputs and use the frequency of zeros to estimate what that probability is. The quantum analog of this is the following. So let Q be a description of a universal quantum circuit, and this maps the 0 state to some new state, U acting on 0. And we define this probability PQ as the probability that when you take this state and you measure the first W qubits, you see the all 0 outcome. And that's given by this quantity here, just the 2 norm of we're projecting the first W qubits onto the 0 state. And of course, we don't have to just consider the 0 outcome. We could ask for arbitrary length W outcome X, and we get some probability distribution P of X. And this defines the quantum output distribution. Okay, so based on these, we can define a bunch of simulation tasks. And I've got 5 here, but even though there seems like a lot, we can kind of break these down, and some of these are actually, let's say task 3 is going to be the kind of key one that we're going to talk about a lot. 4 and 5 are also important. So these are the kind of important ones. But 1 and 2 are kind of there for context, because maybe some people might be more familiar with these. So these can get broken into these 3 categories. And the first one is, so you're given some description of a classical circuit, and you have to decide with high probability whether this classical probability up here is less than 1/3 or more than 2/3. So you're promised that it's either one or the other, and you have to decide which it is. And you should also do so efficiently, so in polynomial time. And so this problem is BPP complete. It's essentially the definition of BPP. And so this can be solved by a probabilistic Turing machine. And the quantum analog is number 2 here, which is kind of very similar. You're given a description of a quantum circuit. You measure only 1 qubit, and you have to decide whether the probability is less than a third or more than 2/3. And this is essentially BQP. And now we have these kind of slightly more complicated analogs, like a function problem analog and a sampling problem analog. So point 3 says you're given a description of a quantum circuit, and you can measure any number of qubits, and you want to output an estimate of the Born rule probability. So this p hat is an estimate of the Born rule probability, PQ. And what you want is that your estimate is epsilon close to the real thing with high probability. And some details about what we mean in terms of efficiency, but this is kind of the quality of estimate you want for a Born rule probability. Again, this is a problem you can do with a quantum computer. That's why it falls in this kind of category. And it's clear that if you could do this problem, then you could kind of estimate PQ to a good enough precision to be able to distinguish between a third and 2/3, and hence solve the problem above. The problem number 4 is a sampling type problem. So you're given a description of a quantum circuit, you measure all the qubits, and your job is to output a sample from a distribution that is epsilon close in total variation distance to the true quantum distribution. And this is kind of the natural task that a quantum computer does. I mean, it doesn't naturally. You measure things and you see a sample from the output distribution. And if it was a fault-tolerant quantum computer, then you could achieve this precision or this performance. So everything in these, 2 to 4 are all things that you could do with a universal quantum computer. And number 5 is quite a way beyond that. So number 5 says you have a description of a quantum circuit again. You measure some number of qubits, and you're required to output a Born rule probability again. So it's a similar type of answer to point number 3, except you want the precision to be multiplicative. So you want to be within epsilon factor of the true probability. But the true probability could be exponentially small, which means when the probability is really small, you need this thing to be super accurate, or this estimate to be super accurate. And this class of problems is sharp P hard. And so kind of it could be used to solve some really hard counting problems that are well beyond the reach of quantum computing. Okay, are there any questions about this before I move on? I know I've gone through it a bit fast, but it's not super important to get all these details of these definitions, just to kind of get a feel for how different they can be in computational power.
I think it's okay.
Okay, great. Let's see. Okay, so I'm just going to focus on the quantum tasks. And I'm going to say that, of course, we could generalize this a little bit by not just kind of not just considering universal quantum circuits, but instead we could replace this by some class of quantum circuits that might be a sub-universal. So something like linear optical networks or something like that, that's sub-universal. And then you could kind of, again, define all these tasks and ask how do they compare to each other. And so this is this becomes kind of the more general problem that we were looking at here. And so in this setting, in this paper, we showed that all these problems obviously get harder as you go down the list. And in particular, if you had an oracle for doing one of these, you could always do the ones above using this oracle. But also, interestingly, we found examples of families of quantum circuits where there is a strict separation between these two tasks, in the sense that you could classically efficiently solve task number 3 for this class of circuits, but we showed a hardness proof for sampling from the output of this class of circuits. And in particular, this class of circuits was later called Clifford magic circuits. So these are circuits where you can input a arbitrary product state, so including magic states, and then all gates are Clifford gates, and then you measure at the end. So there's no classical conditioning allowed, but you can input magic and then have Clifford gates. So this set of circuits can be efficiently simulated classically in the sense of number 3, where you can compute all these Born probabilities to additive precision, but it's hard to classically simulate in the sense of number 4. There's always modulo some complexity theoretic assumptions, but details are in this paper. So, but that's kind of a high level of this result. And I want to maybe just also speak a little bit about, different papers and how they relate to these notions of simulation. So in particular, this paper from 2015 and this more recent one from 2021 were both concerned with notion number 3, this additive error Born probability estimation. And this star indicates that this is kind of the state-of-the-art algorithm for doing this kind of task. For notion number 4, the sampling problem, there's this Bravi-Glossop paper from 2016, this Bravi et al. Paper from 2018, and this paper by Seddon et al. That James talked about a couple of weeks ago. And these many of these are based on these stabilizer extent methods, and I should say this up here is kind of this quasi-probabilistic method that is also a stabilizer extent method and really shows the connection between these two things. And then when we look at task number 5, these 3 papers are kind of dealing with task number 5. So this Bravi-Smith-Smolin 2016, this result was later improved by Kochia, and then Hamam and David Gossett and I did this 2020 improvement. And these were all stabilizer rank-based methods where you're doing like exact decompositions of T-gates, and so you can compute exactly Born probabilities by the sharpest kind of known decompositions of T-gates. And so that's some context for how these things relate to each other and what these different simulators do, or focus on, what notions they focus on. Before I move on, is there any questions?
I'm good.
Great. Okay, so I'm going to move to part 2, which is this constructing these general quasi-probabilistic simulators. So first, I'll kind of do a high-level definition of the task, or what is the goal we're trying to achieve, and then I'll kind of introduce how these simulators are constructed. So because they're very general, we need to first make a bunch of choices to actually get a simulator. And so the model is kind of the is the set of choices you have to make before you have a specific simulation algorithm. And I'll describe this, then I'll talk about the method, which is how the simulation algorithm works, and we'll talk about efficiency constraints, and finally I'll go through a number of examples. And this will this is kind of these general techniques that I've been playing with and trying to see how through all these choices one can come up with interesting new simulation algorithms that perform well, and how these choices relate to each other is kind of something that I'm just toying with and exploring. Okay, so what is a simulation task? We'll be given some gate set, so maybe the Cliffords, maybe Clifford plus T gates, or Toffoli plus Hadamard, or whatever you like. And then we'll be given some circuit that starts with some initial state psi 0. So here I've just drawn the all 0 state. And then it gets acted on by a sequence of unitaries from the gate set. And at the end, we're measuring the computational basis. And there's an outcome of interest that we want to compute the Born probability for. And there's some projected pi that's associated with projecting onto that outcome. And so just some notation here. I'm going to use U to denote the product of all these unitaries. And also, I'm going to be agnostic here about whether I'm working in the pure state formalism, where psi is a ket, or in the mixed state formalism, where psi is a density operator. And for that reason, I have to use this, I'm going to use this weird notation where I say U acting on psi, and this will denote U multiplying a ket psi if we're in the pure state formalism. But in the mixed state formalism, it'll denote our density state psi being conjugated by U. Okay. And so, given this circuit and this outcome of interest, our goal is to estimate the vulnerable probability associated with the outcome pi. And that vulnerable probability could be written as like the length of the projector acting on psi 0 evolved under U. And specifically what that looks like in the pure state and mixed state formalism is we get a psi 0 conjugated by, left multiplied by U, acted on by pi. This is some ket, and we take the 2 norm and square it. In the mixed state formalism, this is a trace of a density operator conjugated by U multiplied by pi. Yeah. Okay, cool. Okay. And so now I'm going to define this model, and bear with me if you haven't seen this kind of stuff before. It might look like, well, I mean, you might be wondering why on earth I'm doing what I'm doing, but it'll become clear fairly quickly, I hope. So we have to choose we have to make a bunch of choices before we can actually construct a simulator, and the first of these choices is to decide a base field, K, and that will either be R or C. And then we have to kind of choose whether we're working in the pure state or the mixed state formalism. And this basically amounts to choosing your Hilbert space. Are you going to be n qubits, a ket, or are you going to be n qubits represented as a density state? And in addition, we have to choose something called a frame, which you could think of as an overcomplete basis, which is an overcomplete basis, essentially. So I'm going to denote the set of frames by this mathbb B, and the elements by the mathcal Bs. And these elements are going to range over this capital lambda, which it'll be helpful to think of lambda as a phase space. So there's some phase space, and there is an operator Bx associated with every point x in this phase space. And the requirement of these frames is that they span the Hilbert space over the field. Okay, so in addition to choosing a frame, I have to choose a pair of maps, and they do the following. So the first map maps elements of the Hilbert space to the probability simplex over our phase space. So in particular, it takes a psi and it maps it to a probability distribution over the phase space. So for every point in the phase space, we get some positive real number, and the sum of them is 1. I should say non-negative real number. And there's a complementary map F, which maps the Hilbert space and points in the phase space to elements of our field. And so it takes this state and a point in phase space, and it gives you some number, it spits out some number. And the requirement is that this choice be such that the expectation value of this constant times our phase point operator, when the phase point operator is sampled with respect to the probability distribution, this expectation value should be psi. All right, recall this F and this probability distribution both depend on psi. And when you take this expectation value, you should get psi. So
can we think of F as a dual frame, or is that something?
No, it's not. It's not a dual frame yet, but dual frames will come soon.
Oh.
But F is just a constant. It's not an operator. It's just some number it's a scalar.
See, but you can obtain it from a dual frame. I think is that.
Yes,
okay.
That's right. I mean, actually, in fact, what you obtain from the dual frame, I mean, we'll see this in the very next equation, is the product of P and F. So we said earlier that the frame is spanning. So every element of the Hilbert space can be written as a linear combination of elements in the frame. And so any psi could be written as a linear combination of these B's. And so this product here is just the coefficient for this B in the expansion of psi. And so that coefficient can be derived from the dual frame. But then you have to kind of take this coefficient and split it into two pieces. So it's going to be a product of a probability and a constant.
Oh, okay. So you're taking the polar decomposition of the okay, yeah, I see. Sorry, never mind.
Yeah. So yeah, I think this equation makes it super clear, right? I mean, it's just a definition of an expectation value plugged in, but you see that you can just think of this product of P and F as the coefficient for X, and then all you're saying is as long as that product gives you the right coefficient, then you're going to be good. And the question is, how do you split that coefficient into a probability and a scalar multiple? Okay. So let me just kind of step back and recap. This is the model. There's a bunch of choices to make in this model before we have a simulator. Those choices are, choosing some field, choosing a set of operators, a frame for your space, and choosing kind of these two maps. And in making this choice, you have to make sure that this equation is satisfied. And if you do that, then things are good, and we're going to have a simulator. And let me show you what the simulator looks like when you make these choices. So there's going to be 2 bits. I'm going to show you how the one sample algorithm works. And this is kind of this is going to be sampled a bunch of times. And then we'll see how what the multi-sample algorithm does with a bunch of these samples. But for now, let's focus on how one sample goes. So we initialize some number F to 1, and we set our state to psi 0, the initial state. Then for each of the unitaries we're going to apply, from 1 to L, the last one, we do the following. We take our state, we apply the unitary to it, and we get a new state. Then we sample a phase point based on the probability distribution constructed on that current state. In addition, we compute this scalar constructed corresponding to that state at that same the phase point, which we sample, and we multiply that into our state to be the phase point operator corresponding to we sampled in step 4. And now we go back. This is our new state. We apply u to it again and repeat. So I've got a little diagram here that might help see this a bit better. So we start in psi 0, and we're going to apply u1 and then u2 and u3 and so on all the way to ul. Obviously, keeping track of these states as we go along, they get more and more complicated because we're just adding more and more unitaries to them. And it's hard to keep track of them, in a useful way, like beyond just the gate sequence description of that state. It's hard to kind of keep track of, have a useful description for this state. And we're going to use these phase points and these operators attached to these phase points to kind of keep track of this state. And we're going to push the hardness of it to probability land, where we don't have to remember everything. We just kind of trust that expectation values will concentrate and deliver what we need for things to work out. And so the way we do this is the following. So we started with psi 0, and we applied u1 to get psi 1, and we've just done this step, and we have psi 1 here. And instead of remembering psi 1 going forward and applying u2 to it, what we're going to do is sample a phase point. And let's call that x1. When we sample a phase point x1, we're no longer going to represent psi 1 as u1 acting on psi 0. We're going to represent psi 1 as the phase point operator at x1 multiplied by f at x1. And based on this expectation formula we had earlier, on expectation, this is going to be psi 1. And this thing we're going to kind of treat as our new state, this phase point operator. And when we apply u2, we apply u2 to this phase point operator. And now we get some new operator, but this is going to get complicated real quick too. So what we do is we sample from this new operator to get a new phase point operator x2 and a new factor f of x2. And now our psi 2 is going to be represented by this times this f of x1 that we already had from before. And we just keep going along doing this until we get to the end. And by the end, we're representing psi L by the phase point operator at our last phase point that we sampled times a chain of these f's, one associated with each of these jumps. Okay, so the key to why this works is really this equation here that says the expectation value of this f times b is psi. And so we want to kind of use this argument, and this is like a one-step expectation value, but we want to use this argument to show that, in fact, this f times this bx is going to be the expectation value of psi L. I mean, the expectation value of this is going to be psi L. So let me say that again. I'm going to show that the expectation value of the f that's output here times this b, the last phase point operator that's output here, which is bl, is going to be psi 0 multiplied by all the unitaries. So it's going to be psi L. And how does that work? Well, let's just expand out what this is. Well, this f is just the product of all these f's. And this BL just is the BL. And what do we mean when we take the expectation value? We're taking expectation value over all points in phase space according to their probability distributions. And since these are all independently sampled, we could just start by taking expectation value over XL. So we're taking an expectation value of this guy over XL, just these two factors, and the rest are untouched. And when you do that, you recall that this was the operator that came before, which was UL applied to the phase point operator at XL minus 1. And now this U is, I mean, it's linear, so we could just push this U out. And what we're left with before this U action is this U is going to act on the expectation value of this string, which is identical to this expression up here, except it's got like one less phase point in its one step shorter in its path through base space. And so, basically induction, and you get a UL and a UL minus one and so on, all the way to our psi zero. And so we have our result, which says that the expectation value of the product of these is psi L, our final guy. Okay, that's great. And how do we use this now in our multi-sample algorithm? So basically what we do is we call this S times. So we take S samples. So for I equals 1 to S, we call the one sample algorithm, and we get an F and a B, and we multiply them together to get a one of these representatives that on expectation is right. And after we get all S of them, we average them. And we get this thing psi bar, which is just average. And then to compute an estimate p hat, we just compute the length of the projector times this average, which is I mean, so what we're doing with average is exactly what we would do with psi L if we had psi L. But we don't have psi L. We have this kind of average, and we're going to make arguments about concentrations to show that this average is good enough. This concentrates fast enough that we can do whatever we want. Okay, so yeah, I'm just going to kind of keep this formula up here, and say the concentration tells us that this is a result, that the probability that p hat minus p is greater than epsilon is exponentially suppressed. So it's like an exponential in, it's e to the minus something bigger than s epsilon squared on m. So this is positive. So s is the number of samples. So as the number of samples grows, it becomes exponentially unlikely that you will your error will be bigger than epsilon. But obviously, if you make epsilon small, then you have to make s large to fight with it. But the other key factor is this m that's competing with the number of samples. So as m grows, you need to grow the number of samples. And what is this m? Where does it come from? M is basically the maximum Born probability you can, or the maximum p hat you could get when you just use one sample. So it's the maximum of frame element times these f's times pi, take the 2 norm square in the pure case, or the associated quantity in the mixed case. So you can see that these f's multiply into each other. So if they're 1, you're good, everything works fine. But if they're larger than 1, as they multiply, they can grow exponentially in the number of gates you're applying. And that would mean that your sample complexity has to grow exponentially in the number of gates you're applying in order to make sure that you can do this task. So I should say this first version of the concentration, this pure state version, you could find in this paper, and the mixed state version you could find in this 2015 paper, and I guess you could find both in the PhD lists. And I should also say that there are distinctions between the pure state formalism and the mixed state formalism. So in particular, the mixed state formalism can give you worse performance, but it can sometimes be maybe easier to simulate. So for an example is here where B is like one of these frame elements, might be psi in the pure state, and the corresponding mixed state guy is this outer product. When you compute these m's, you get a square here in the mixed state that you don't get here. So, but more generally, you can have quadratically worse performance in S in the mixed state formalism. But on the flip side, in the pure state formalism, you might have to simulate phases, which can be difficult. There's other challenges with pure state formalism. Okay. So we've kind of like painted this picture of, or described these simulation algorithms, but we haven't really talked about efficiency, and I want to kind of nail down what are the key constraints that they need to satisfy for efficiency. So these are the steps of the algorithms, but they're not all easy to do. So one thing we have to kind of be careful of is step 4, where we have to sample a point in phase space. In general, phase space can be very big, and it's not easy to have a scheme for sampling from that particular probability distribution. So you have to have a efficient way of doing this in order for this simulator to work. Function might not be trivial. It might be hard. Additionally, if these Fs grow too fast, then your simulation is has really poor sample complexity. And finally, we have to be able to kind of compute this function on this average, and that's not. So this here is basically a summary of the key kind of hurdles that your simulator has to overcome: sampling, computing F, M not growing too quickly, and being able to compute this this length formula.
I think last time we learned about these dyadic simulation, right? Yeah.
Mm-hmm.
So that, I mean, is that because in the previous slide you were taking the states to be the same, like 5, 5?
Yeah. The issue remains in the dyadic setting. To be honest, the previous slide was it's like a kind of toy way to see this, but even if you kind of do cleverer things to avoid the square that appears in the previous slide, you will still run into issues. Even with like dyadic simulation and stuff, you still have worse scaling. I think there are details here that are still not clear to me, and I would like to nail down and have written in a paper, just so that they're all all the I's are dotted and the T's are crossed, because I think there's some subtleties in how these things relate to each other. But the mixed state formalism is quadratically worse in general. I think possibly even provably.
Okay, thank you.
Okay, so I want to talk about some examples now. And my first example is almost, it's not really an example, it's almost a formula for generating examples. So let me go through this. This is for the pure state formalism. So we choose a base field, our base field to be C, and for a suitable group, we choose we set these UGs to be a unitary representation of the group. So each of these UGs relates to one of these group elements, and we choose the frames to be this unitary representation acting on the all zero state. And we'll have some function alpha that takes group elements to C. Maybe don't worry too much about this for now. You could imagine it's 1 for now, just constant 1 all the time, so we can just ignore these alphas. But you can kind of choose these things such that the outer product of this frame element summed up gives you the identity. And if this is satisfied, then you can define your P function and your F function exactly like this. So your P function is basically take your psi and act on it with the bra frame element, and take the modulus, and you have to divide by some normalization constant that maxes the probability. So obviously the top is, non-zero positive, and normalization constant just has to be the sum of the top over all G. So here it is. It's the sum of the top guy over all G. And what does F do? F basically just puts in the phase, so that the product of P and F is the numerator without the absolute values, without the modulus. So you can see that this n here is going to cancel this n here, and then this is just a phase of the thing in the top. So when you multiply them, what happens? Well, let's check that this expectation value equation is satisfied. So the expectation value is going to be P times F. What is P times F? Well, it's just alpha G times this thing without the absolute value. And we're going to multiply it by the frame element. And this is the frame element here, right? And you can see that just if you took this and put it here, you'd see that you get this sum here is just identity. And so you get identity acting on psi. And so the expectation value is psi. Okay, so this is so this says, like, if you choose your P's and F's this way, and you have your frames structured this way, as long as this equation is satisfied, everything's going to work out. So let's kind of do our first real example where we make these choices. I'm going to choose the group to be Z and D under addition, or ZD to the N under addition. And so the unit representation is just going to be like Pauli X strings, or generalized Pauli X strings if we're dealing with qubits. And so the frame is just going to be these guys acting on the zero. So it's just going to give you all computational basis states for n qubits. Then we just set alpha to 1 here. And of course, this sum is just going to be a sum over all computational basis states, and it is the identity. And these probability is P and F reduced down to these simple expressions, where P is basically just the modulus of the overlaps with the computational basis. F puts in the phases, and this normalization, which is also kind of a pure state version of the negativity, is just the one norm of the coefficients in the computational basis. Okay, so let's kind of now say, well, okay, all right, the thing kind of works, right? But what about efficiency? What about performance? Let's look at this. When would you use this? And a kind of a good gate set where you might use this is the Toffoli plus Hadamard, and the so let's talk about can you sample X from this probability distribution? Yes, you can. I mean, it's a product basis. When you act with a Toffoli on computational basis states, you get computational basis states. So there's really nothing to sample, because I mean it's deterministic. You just do a deterministic transition. When you act with a Hadamard, all you do is turn one of the elements in the string into a plus or a minus, and then computing these overlaps and defining these probability distributions is like a 2-outcome distribution. So it's kind of easy to sample from. The same goes with these Fs. And then we can ask, well, how does M grow? Is M okay? Of course, for the Toffoli, the negativity induced by the gate is just 1 because it's deterministic. But for the Hadamard, we can have these like 2 outcomes, each with a weight of 1 on root 2. And so when we sum them up, we get 2 times 2 on root 2, which is just root 2. So we have to pick up this factor of root 2 with every Hadamard we do. So Toffoli's are free, Hadamards are expensive. So I mean, qualitative, I've given it a red tick because I couldn't decide if it's good or bad. And you can compute the Born probability, like taking these lengths over the average. That's efficiently doable. So that's kind of this first example. The second example is a little bit more interesting, I think. So here we take the frame to be the set of all strings of 0, 1, plus and minus. So it's like tensor product of Z eigenstates and X eigenstates. And in this setting, there are many choices of alpha that ensure that the sum over all these is the identity. And I should say it's important to note that we're not committed to our choice of alpha or P or F throughout the entire simulation. We can change this at every gate. And so we can gate by gate optimize our choices to minimize the scaling of M, which is what well, I guess here we didn't really have any choices, but we'll see. We might see examples of this later. So again, kind of natural setting for this is the Toffoli plus Hadamard gate set. And in this gate set, again, sampling is easy. Computing these Fs is easy. And if we want to know how M grows, we'll first note that now the Hadamards are free because this basis is preserved under this frame is preserved under the Hadamards. There's deterministic action on them. And this CCXs now have a cost, but their cost somehow depends on what this frame was. And you can kind of choose these, and you can see that you can get one of these 3 different costs depending on the frame. And the frame is somehow, you don't always have a choice of what frame you end up in, but you have some choice. You can kind of there is some choice in which frame element you choose or which decomposition you choose based on these choices of alphas, and you could hope to kind of guide your algorithm to the best choice for the upcoming structure of CXs. But even if you don't do any of this and just kind of ignore it and choose things randomly over a very long sequence of gates, you'll find that the geometric mean of this negativity contribution is around 1.09. So basically, on average, your Toffoli's cost you a factor of 1.09, and comparing this to like state-of-the-art Clipper plus T simulators, where they need to use like 4 T gates to synthesize a Toffoli, that cost would be 1.37, which is obviously a lot higher. So I think this is kind of interesting, and maybe I've been a bit conservative in giving it a red tick. Maybe it should be green. And this last thing could be done as well. So that's kind of example 3. I'll do one more example with a kind of Clifford type frame in the pure state, and then we'll look at a couple of examples in the mixed state formalism as well. So in this pure state formalism, we have All right, I see we only have about 5 minutes left, so I will try to kind of go a little bit quicker.
It doesn't have to be, no, it can go to 4. It's up to you. Of course, you can end earlier, but we have up until 4.
Okay, great. So here we're going to choose our group to be ZD to the N under plus. I think I'm going to very quickly probably assume they're qubits anyway, so maybe just set D equals 2. And we're going to choose C to be some element of the Clifford group and keep it Clifford group. And again, this choice C is not going to be fixed throughout the simulation. We could vary it gate by gate. We're going to set our unitaries to be, these Pauli X strings conjugated by C. So it's just like just a basis change. And so the frames are going to be they're basically the computational basis acted on by C. Because as you can see, like when UX acts on C, this dagger cancels that one, and then you get a computational basis, and then it's rotated. So these are the frame elements, and of course set alpha to 1, and you're going to get this equation is going to be satisfied because you're summing over a computational basis, and we get these maps. And now our negativity or our normalization constant becomes psi acted on by our choice of C, overlap with basis states. So we can kind of always take C to kind of send psi to 0, to the 0 state. So if psi was a stabilizer state, we could always send it to the 0 state and get like deterministic transition. So here a natural gate set would be something like Clifford plus Z rotations by some angle theta. And again, we can, this sampling is kind of easy enough to do. Computing F is easy enough. And if we want to look at how this M scales, we note that for Cliffords, because we can always set the C dagger to kind of cancel whatever Clifford we were applying to whatever stabilizer state, we can always, this psi is always going to be like a frame element, except at the very beginning, which, is still a frame element technically. And so this is going to be a stabilizer state, and we can always choose C to send that to 0, and then only X equals 0 will contribute a factor of 1. Now, if we have a Z rotation, things aren't so clean, and we get some contributions from the rotation, and we get some messy equation. Here's a plot of what that looks like when you go from 0 to pi on 4, which is the maximum. So here's the curve. The modern state-of-the-art algorithms will do something a little bit better, which is this blue curve. So in this paper with Oliver Reed and Smith, Camille Koshak, and Stephen Bartlett, 2021, we did like a bond rule probability estimator. And these are kind of stabilizer extent-based quasi-probabilistic methods. And this Ravi Brown, Chaplin, Campbell, Gossett, Howard, 2018 paper, again, a stabilizer extent-based method that kind of achieves this sharper runtime. So maybe it's not state-of-the-art performance, but it's still pretty good. And something like this, maybe 10 years ago, would have been state-of-the-art. So, and for small angle rotations, this can be super useful. So if you're getting like small coherent errors on a stabilizer code or something, and you want to analyze how this performs, you can classically simulate it and say useful things about it. Again, computation of these lengths is efficiently doable. So that's this example. I'm not going to talk more about this, but you can kind of keep beefing this up. You know, you can go to like full set of stabilizers as your frame, and then make kind of fancy choices of alpha in order to get performances that scale more like this state of the art. But you know, this is just an endless game one can play. I want to talk a little bit about these mixed state formalism. Here, you know, again, there's a recipe, and it's quite similar. And now we choose our field to be C, and more commonly it'll be R. And our frames are going to be denoted by B, and we'll have a dual frame denoted by D. And these both live in the Hilbert space. We need to kind of satisfy the property that for all psi in the Hilbert space, psi can be written as a sum of trace of psi being hit by the dual, the dagger of the dual, times B. You know, if you stare at this, this is essentially the same equation as we had before, when we're saying, you know, this thing I equals the sum of these elements. It's basically, you know, if you think of this in terms of super operators, you're really just saying that you know, the action of D and B on psi is the identity in super operator language. So and then we choose these pair of maps to be the absolute value of the coefficients in the frame, normalized, and this is just a phase again. Okay. So my first actual example is just a Pauli frame, and really the behavior is very similar to what we saw with the computational basis frame. I mean, so we have a Pauli frame now. These B's are just n-qubit Paulis, and the dual is just the Paulis, but with this prefactor of 2 to the minus n. And of course, we can write any state as kind of in this Pauli expansion using this equation. And now these probabilities are the absolute values are associated with the Pauli coefficients of the state. And the normalization is the one norm of the Pauli coefficients. So again, if we look at the gate set Clifford plus T, you know, sampling is easy. The Pauli frame is a product frame, so everything's kind of, you know, if your gates are acting like one or two qubit gates, everything's like contained, similar with this F. And of course, Cliffords are going to be free because Pauli is transformed deterministically under the action of Cliffords. But T gates will cost you a little bit. So a T gate will take a Pauli X to 1 on root 2 times X plus Z, X plus Y. And so you get 2 Pauli operators that overlap and give you a factor of 1 on root 2 each. And you get this root 2 factor. And so the performance isn't great on T gates. In addition, the computation here can actually give you large numbers as well, which contribute to M. And because we're kind of carrying things in a Pauli frame, if you at the end you're kind of going to need to do something like pi times psi L when you're computing your vulnerable probability, but psi L is now going to be represented by Pauli, and so this trace can be exponentially large, which is bad. But you know, if you modified the task a little bit and said, well, maybe I'm interested in estimating operators that have a small 1 norm in, you know, Schatten norm or something, then you could kind of use this procedure to do that task. So estimating expectation values of certain observables, like for example, estimating, trace overlap with another state. Okay, so my last example is not really super well thought out, but I thought it'd be more interactive, because I thought I might try to give as an example the lambda polytope, right? And then we'll kind of talk about it, and maybe there's probably a bunch of stuff I don't understand about it, so you guys can chat to me about it and tell me where I'm wrong. So here you choose your base field to be the reals, and you define your frame operators to be the vertices of this convex set, which are the set of Hermitian operators, such that for all stabilizer states, sigma, the trace overlap is non-negative. Okay.
Are you not including the trace one condition, or is left out for purpose?
I guess 1 minus this should be. I mean, I thought somewhere there was a pi. Okay, I think I just assumed that whatever pi is, I minus pi will also be like a valid substitution. So if it's more than 1, then you should run into trouble there.
Yeah, I was just saying, I think you need to include the trace one condition, otherwise you will get like a cone of the polytope, right?
Oh, sorry, you're saying that the frame operators at trace one. I see. Yes.
That's what I was saying. I mean,
Yeah.
if that's
Okay.
is left out for purpose or not. Okay.
Yeah, no, sorry, no, it's the purpose is simple. I've forgotten to include it. But yeah, okay, let's put in that condition, then it's trace one. And we have to choose a dual, and obviously choosing a dual will not be easy, but we know that one exists, so let's just assume we have one. And then we define these maps. So these are just the coefficients of the state in in this vertex expansion. So here the kind of gate set, or the setting is you have T states as a resource, and then all your gate set is Clifford's. And you can do classical conditioning. And so you want to kind of look at it in this setting. So there's kind of two things to consider here. Because we're starting with the state resource, there's the first step is sampling like to get from the state to your frame element. And then once you're in a frame element, you still have to sample each time you act or change your frame element with gates, or if you're doing measurements throughout. So I'm going to kind of reserve this for like we already have a frame element and we're going to do the actions. And I think there's a more subtle cross here. I mean, I guess the issue here is that while the action of, say, Clifford will take a frame element to another frame element, there's so many frame elements that maybe we don't actually know which frame element we went to. We can't keep track of. We can't index these, so we can't actually accurately represent what frame element we're in. I'm going to say that you can compute these Fs because they're essentially going to be 1 for now. Because because when we act with Cliffords on the frame, we just pick up a factor. I mean, it's deterministic. So and these Fs are just the coefficients, so they're just one. How does M scale? Obviously, everything is one because of this, and the measurements as well have the same property. I've written that out. And can we compute this average? I mean, we kind of run into this problem of we can't really compute this quantity here, like a trace of a joule with a frame operator, or with a projector.
One second. Yeah, I guess I have a question. In the second line, psi equals sum over trace bx, right? The bx's here are going to be vertices of this lambda polytope. So we know that trace psi times the dual is positive, right? This is a convex mixture.
Trace psi times the joule is positive. Yes, this here.
Well, yeah, I'm just looking at the second bullet point.
Mm-hmm.
Yeah, so it should be a convex mixture. So these traces, trace psi dx dagger, should be some positive number, right? In fact, it's a probability distribution.
Yes. Yes.
So taking the absolute value won't matter. Shouldn't n be trivial? Am I wrong? Isn't it?
N is trivial, but the actual value here, for a particular x, is hard.
For a particular x, yeah. So you're talking about for the px part, that will be difficult to know. Yes.
Yes, for the px part.
Because n will be easy to compute, I guess.
N will be 1.
Yeah.
Yeah.
Sorry, I have a question too. Are these dual frames easy to compute for a small number of qubits? Did you ever check what they're for the lambda?
Yeah, I mean, do you mean for the lambda polytope, for like
yes.
this actual frame?
Yes, exactly.
I mean, I think these dual frames, I mean, they're non-unique, so there's lots of choices, and you can choose this dual frame gate by gate in the more general kind of setup to minimize your normalization constants or your negativity or whatever you want to call it. But in this setting, things are free. And so I guess you probably don't have to worry too much about how you choose your dual frame. But I mean, even if you define your dual frame to be be the self dual frame or something, so up to like a renormalization of the B's, like proportional to the B's, then I mean, you'd still be kind of stuck with having to compute the trace of bx times pi for some projected pi.
Trace of bx times pi.
So you have some frame operator bx, and you've kind of gone through your procedure, and at the end, you're at like your last phase point is x, and you have some base point operator bx. And now what you need to do is compute your Born probability. So you multiply it by pi, and you take the trace. And doing that computation is not clear. I mean, you could do it for like a small number of qubits, but to do it efficiently as n grows is
Oh, okay, yeah. So
I don't think
essentially
it's
you would
still-
need to know what the update rules are because trace of bx psi is just, or sorry, trace of pi bx is just going to tell you the outcome of a Pauli measurement. So if you don't know the update rules, then you will not in general know that one either.
Mm.
I have a silly question. Sorry, you said before you could take it to be the frame to be self-dual.
Mhm.
That's always the case, or
Uh,
the reason I asked that is because I don't know why when I was looking at this paper, this review article by Ferry and no, not a review article, just this paper about frames by Ferry and Emerson. Don't they have some sort of result about both the frame and the dual frame can't have like positive, they can't both be positive, or let me look up the exact statement. And in this case,
But I think you need when if things are over complete, I think it's fine. But in that case, I think they take a basis like that's not over complete, I guess.
I thought it was a general result for frames. 1 second. Maybe I'm misstating the result one. Sorry.
do they mean like in the convex hull?
There does not
Like-
exist a dual frame of positive operators for a frame of positive operators. I guess these are not positive operators. Okay. Okay, sorry. Yeah, no, that's not quite what the statement is. Okay, never. So the confusion was the following, that I knew that these coefficients were positive, so I knew that there was something in the statement of the theorem about positivity. So I was wondering if maybe that would exclude. Anyway, I don't think it holds.
Yeah. I'm gonna just say like one more 2 cent comment, which is if we now consider how to transition from the initial state, which is maybe like some magic states and some and we want to like do that jump from the input state to a frame operator, then we again need to sample, and this is kind of tricky because these frames, if you work out a frame decomposition for like 10 qubits, then you can't do it for 11 qubits, and so there's no kind of efficient way of constructing these probability distributions. And similarly for computing these F functions, I believe.
I see.
And that's exhausted my what I have to say about this setting. But so some open questions. I think one interesting question is, how do you choose B for different gate sets and for different circuits? And in particular, can you exploit symmetries or known properties of a circuit to make better choices of B? So I think, ideally going forward, that there'd be these like kind of clever tailored algorithms that vary all these things with the details of the circuit in order to really optimize. And right now we have a much kind of simpler version of much simpler simulators. There's also this question of how to optimize the decomposition in B. And we know that like there's kind of there's a convex optimization problem, but it's in exponentially many variables, and so you have to kind of to something that's like suboptimal. There's also this kind of question of how to optimize these probability distributions. There is a kind of for like a fixed decomposition and B, and there is like a kind of global optimal probability distribution to sample from, but that can be hard to sample from, and then the local optimal probability distributions, which are easy to sample from, are not globally optimal, and so there's kind of a trade-off figuring out how to do this best. And there's also this kind of problem of like lifting these estimators of vulnerable probabilities to sampling algorithms. And I think this is very much doable, and just kind of needs a bit of work. And that's all. So I want to thank you for your attention, and if you have any questions.
Thank you, Hakop. That was very nice. I appreciate that you put in the slide about Lambda. That's interesting. Any questions?
Can you say a bit more on this last point you said, lifting these to approximate sampling algorithms? What do you mean by lifting here?
Yeah, so I mean, like, in part one of the presentation, I went through these notions of simulation, and notion number 3 was like, estimating vulnerable probabilities, which is what all these generalized simulators are doing. They're estimating this like probability of seeing some outcome associated with pi. But notion number 4 or something was like sampling from the output distribution of the quantum circuit, or approximately sampling from the output distribution of the quantum circuit. Mm-hmm. And a sampler can be used to estimate the vulnerable probability, but it's not, and sometimes the vulnerable probability estimator can be used to sample, but this kind of requires an additional condition of sparsity or something like this. But I think the simulators that we're constructing here could be used to construct sampling algorithms, not just vulnerable probability algorithms, not just vulnerable probability estimation to additive precision.